In this problem, we're asked to find the wavelength of an object whose mass is 2.3 grams and which is traveling at a constant velocity of 35 meters per second. We know that whenever we're asked to find the wavelength of an object and we're given its mass and the speed at which it's currently traveling, we could use DeBroglie's equation, which states that gamma, which would represent the wavelength of any object, equals h, which is Planck's constant, over m, which is its mass, times the velocity of that same object. So right off the bat, we know that h is Planck's constant, and we know that h is 6.6262 times 10 to the negative 34 joules seconds. So this is joules times seconds. We know that whenever we're given something in joules, we're going to be dealing with kilograms within this complex unit right here. But the only problem that we actually have here is that we're given the mass in grams instead of kilograms. So essentially all we need to recognize is that whenever we're going from grams to kilograms, we're simply going to be multiplying by 10 to the power of negative 3. So right now we could just set up our equation. We could say, okay, gamma equals h, which is Planck's constant, which is 6.6262 times 10 to the negative 34. A joule second, well, first of all, a joule is kilogram meters squared per second squared. So we know that a joule second, or in other words, a joule times a second, is going to be kilogram meters squared per second, right? Because we had second squared, but now because we have a second on top, it reduced down to 1 over second. Alright, so now on the bottom, on the denominator, we have mass times volume. We've already got mass in terms of kilograms, as we just said. 2.3 grams is the same thing as 2.3 times 10 to the negative 3 kilograms times the velocity, which we already have. We know that this is going to be 35 meters per second. Just using dimensional analysis, we could see what's going to cancel out. M squared divided by m is just going to be m. We have 2 seconds on the denominators here. This is a complex fraction, so we could just cancel these out. And the kilograms, will also cancel out because we have 1 on the numerator and 1 on the denominator. So now we're left with meters, which is exactly what we want. Whenever we're talking about wavelength, we're going to be talking about a unit of length, and meters, for all intents and purposes in this equation over here, is perfectly fine for that. So now it's just a simple matter of breaking this down and doing some arithmetic operations on it. 6.6262 divided by 2.3 divided by 35. Let me get my calculator out. This is going to be 6.6262 divided by 2.3, and we also have 35 on the denominator here. This is going to be 0.082313. Let me put this on my other monitor so now I can read it off here. 0.082313 times, we have a bunch of exponents here that we could deal with. We have a negative 34 on the top, and we have a negative 3 on the bottom. We know that whenever we're dealing with powers that have the same bases and we're talking about them in terms of a fraction, we could just subtract the exponents. So negative 34 minus negative 3 is going to be 10 to the negative 31. So now what we're able to do here is we could say that, okay, gamma is going to be equal to 8.2313. We just jumped this 2 decimal places. And now because we made this 2 decimal places bigger, we have to make this 2 decimal places smaller. So this is going to be 8.2313 times 10 to the negative 33. And again, we're talking about this in terms of meters.